All right, here we go. Reaction number 17. This, I think, is not a homework solution. I think this is like notes provided for the class, maybe for a flip class. Sounds like we're going to be hearing about sound.
This is Mrs. Mooney's notes for Chapter 12, Sound. Sound waves are longitudinal mechanical waves that are produced by vibrating objects. When an object, such as your vocal cords, vibrates, it causes the air molecules to alternately bunch up or compress and then spread back out. When these trains of compressions reach your ear, tiny bones begin to vibrate and your brain interprets this as sound.
So these visualizations are just so cool, right? Another perfect example of use of video, right? So my question for you guys is, what notes do you expect your students to take when looking at this, right? So obviously you can provide these slides to your students and they can watch these over and over again. When I make this simulation, I actually color one of them a different color so you can realize that there's nothing actually traveling from left to right. They're all just wiggling back and forth. It's kind of hard to see, so if you watch when I turn it back on, try to follow a single dot, and you'll probably lose it when it goes into the compression phase. And it's funny, right, that when you pause it, it's sort of hard to see where the compression phases are, but if you really look, there's one here, one here, one here, one here. But man, when the video's going, do you see it like crazy? And I love this comparison to transverse waves, right? Because these kind of look like air molecules, the way that we're modeling air molecules with black dots, but this is a completely different sort of wave. This is not how sound goes. So I like that. And then I love how she's talking about the small bones in the ear, because you can imagine if there's a teeny tiny little bone right here getting smacked by some air molecules over and over again, you can imagine that it might vibrate. So very cool.
You can see that the sound waves are longitudinal. Look at the direction the material, the air molecules are vibrating. In the same direction as the propagation of the sound wave. Both are going horizontally here.
Cool.
Compared to a transverse wave, where the direction of the wave is horizontal.
You can really see her mouse well.
Vibrating vertically here. So this would
be that's super cool.
Wave. Longitudinal waves, such as sound waves, are made up of compressions, areas where the medium, such as air molecules, are all bunched up. And
this is really cool.
Areas where the...
air molecules aren't springs. But I think that this really can, this one, when we freeze it, we don't have to see the movie. We can, yep, that's definitely the compression phase. This is definitely the rarefaction phase. I hate that word, rarefaction phase. I think that the spring visual really, really helps that, especially after seeing the previous video to understand, okay, it's a dynamic system, but here we're going to freeze it. And if she had frozen the previous one, it would have been harder to see, but this one you can see really, really well. She's coming to it also, but I love finding places to measure the wavelength from, right? You can measure the wavelength from any point. You just need to find the next place where the spring is doing the exact same thing. But, there's some obvious choices, and she's made the most obvious one here, like where it's all bunched together to where it's all bunched together is the wavelength. If you ask yourself, well, where is it most spread apart? Maybe here, and we might not quite be seeing it here. So I think that that's a really great choice of where to draw the wavelength.
Medium have spread back out again, called rarefactions. So, and a wavelength for a longitudinal wave is made up of one compression, one rarefaction, and the wavelength would be measured from rarefaction to rarefaction.
Cool. Right, so what you just said, absolutely true statement. Now you could expand that and say, well, you can measure the wavelength anywhere you want, but you're never going to be wrong if you say measure it from rarefaction to rarefaction or compression to compression. You can just tell them one and say just do it. It'll always work, because if it's a wave, it's going to have multiples, right? If it's like a single event that only happens once, boom, and then gone, well, that's not a wave. There's no wavelength. So whatever's going to work for your students, maybe you do peak to peak, maybe you do zero crossing to zero crossing, or trough to trough. All of those are going to work. You can try to lay it and say, hey, you can choose any old one you want. But honestly, if there's one that really works for students, just let them use it. Because again, the wave, like my hand here, is going to have multiple copies. So that'll always work. I think that's very cool.
As we learned in the last chapter, the amplitude of a transverse wave is measured by the height of the crest, or the trough. The amplitude of a compressional or longitudinal wave depends upon how dense the medium is at each compression. In other words, how tightly packed the material is at the compression area.
Yeah.
This spring here, A, would be more dense than spring B.
So I love this. So it's very visual. Like find out where it's, if it looks more compact, it is a higher amplitude than here. But it's also fascinating to think about like the amplitude of the motion of the individual particles of the spring, right? So you can ask the question, this little particle right here, what the heck, the one that her pointer's on right there, how far has it traveled because all it's ever doing is this, wonk, 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 wonk. And so how far has it traveled? Well, that's really hard to know. Well, which exact loop of the spring is that when trying to do a comparison here? Whereas with transverse waves, you can just put one sine wave on top of the other one. You can say, oh, obviously higher amplitude. So even though the amplitude is strictly a measure of how far the individual particles move, her description of trying to find the density, I think, is way easier visually and communicates the same thing. So I love that.
Because spring A's compressions, the materials are more tightly packed, more close together. Here, the material is a little less dense, a little spread out, so the amplitude would be less. Also, remember, the amplitude is a measure of the energy. So the greater the energy is of the wave, the more tightly packed the material would be in the compression, and the greater the amplitude.
So I really, really liked when she said, and remember, and even on the last slide when she said, remember with the transverse wave. So there's huge connections between all the transverse wave stuff, which is usually, ropes and strings and musical instruments, like string instruments. And then usually the next chapter is these sorts of waves, these longitudinal waves, these sound waves. So much is the same. So use it. When she says, remember, it's really like, hey, you guys, come on. This is not brand new stuff. Use your brains. Let's go. I think that's so great to be able to draw the connections as often as possible.
Sound waves travel through solid, liquid, and gases, the velocity of which would depend upon the density of the material and the temperature of the air. The more dense the material, the faster sound will travel. And here you can see as the density of the material increases, so does the speed of the sound wave.
Very cool.
Also, the higher the temperature, the faster the particles of the medium are
Love
moving,
that.
have more kinetic energy, and will carry the sound faster.
Yep, the individual particles move faster, so it kind of makes sense that the wave would move faster.
The speed of sound in air is 331.5 meters per second at 0 degrees Celsius, and it will increase at 0.6 meters per second per degree. So we'll generally use the speed of sound of 343 meters per second at room temperature, which is typically taken at 20 degrees Celsius. And this value is obtained by 331.5 plus 0.6 times the 20 degrees above zero. Actually, I think
So thinking again about how you might connect to the previous chapter, I love, she's laying out all of these things that we're going to need to know. And she, in the previous slide, talked about, temperature matters, and it's because of the microscopic motion of the particles. Well, this is super important, right? If you're doing calculations, you're trying to figure out, where something is based on how sound is reflecting back to you, that kind of stuff. The fact that the temperature affects the speed is important. And of course, they've seen that in the previous chapter, very likely, because if you pull tighter on a string, the velocity of the wave on the string can dramatically increase. I paused it here because I just wanted to sort of set the stage. This bullet point here, this is exciting and new and absolutely does not happen on strings, right? And so strings are a one-dimensional thing, just a tiny little string with standing waves on it. But this is the new stuff that tends to come in the sound chapter. So I'm curious to see how she sets it up.
You get 343.5, but unless told otherwise, use the speed of sound at 343 meters per second. Sound waves can be reflected. Those are your echoes. Sound waves can be diffracted, which means they bend around edges of objects or through small openings, such as doors, so you can hear people in another room. And sound waves can interfere with one another, both constructively and destructively. Pitch is a measure of how high or
Ooh,
low
different
a
font.
sound is, and it depends upon the frequency of the sound wave. Um, Sound waves that have a very low frequency and therefore would have longer wavelengths would have a low pitch. So low frequency, long wavelengths, low pitch.
I really love how she's emphasizing these adjectives, lower, longer, right? It's confusing, right? Because wavelength and frequency are inversely proportional. When one gets big, the other gets small. And I realize that I have this so internalized that it just makes sense. You draw this and you say low frequency. I'm like, yep, right? And yet what's actually shown are longer things, right? So one thing gets bigger, the other gets smaller. And you just need to develop that intuition. That's maybe not the right word, just basic understanding, right? These exactly as she's laid it out here, low pitch, low frequency, longer wavelength, so small, small, big. I think that we have to do it because we draw so many things. So as soon as you draw it, it tends to be a wavelength. Of course, it depends on the axis, right? So the wavelength gets bigger, the period gets bigger. That's the other thing. I guess that's not, she doesn't have that on here. The period and the wavelength get bigger, and the frequency goes lower. See, I even had to think about it just there. So I think that doing these kinds of examples, and especially with things that they might have some experience with, I don't know if people actually have experience with foghorns anymore, but whew, they probably have experience with screaming people. So I think that these examples are great. I do think that, putting an axis on here can be useful because eventually sometimes they see it as a position, sometimes as a time, but there's a great correlation between those two. They're going to look quite similar.
And you can remember low frequency, low pitch, like a foghorn or a lighthouse horn. Then as the frequency increases, notice the wavelength decreases. But at any rate, high frequency sounds have high pitch, like a screaming girl or a police siren. The human can generally hear frequencies in the range of 20 to 20,000 hertz. Humans cannot hear below 20 hertz. Sounds below this level are termed infrasonic. Infra means below. Sonic refers to sound.
Love that.
Sounds above 20,000 hertz are termed ultrasonic, above sound, although some animals, most notably dogs, can hear frequencies in this range in which you would not be able to hear.
So I was laughing because all of us physics teachers use this range, 20 to 20,000. Super easy to remember. There's lots and lots of really, really interesting things about that range. So first, it says a healthy human ear up to 20,000 hertz. I wonder if you've met anybody who can hear up to 20,000 hertz. There's these great apps out there where you can sort of test your hearing. And of course, you can go to an audiologist. I'm way down, 15,000 is my limit. And the funny story is we have this really great set of bars that are tuned to all be, I think, a C or something. And so they're basically like a little chime. And there's 4 of them. And you just whack it, right? And you say, okay, you guys can hear that. That's 1 octave. And then, okay, here's the next one. That's the next octave. And so I'm in class one day. And I'm showing them this. And I just think it's fascinating because there's also the subtlety that metallic chime-based instruments don't have the scaling factor you're used to with wind-based instruments and string-based instruments. There's like this extra square root on the length that comes into play because the physics is different. So I was just showing how, this is 4 octaves, but we're not getting, the length spacing isn't doing what you thought. Anyway, so I'm whacking it. I'm like, hear that? It's very pure. You can really, really hear that. And the next one, wow, that's a higher pitch. Up to the next one. And finally, the last one, I'm like, oh, shoot, it's broken. And I'm whacking it, and I'm looking at how the string has it hung, and I'm trying to figure out what's wrong, and I'm whacking it like this. And I look up, and the entire class is just like freaking out. And I'm like, what? They're like, can you please stop? And it turned out, man, that one was beyond my hearing. I could not hear that at all. But I could. It was working just fine. So recognize that often you're teaching physics. Physics is most often taught to high schoolers, right? And they have the best chance of being able to hear up that high. I think the other thing that's fascinating is the phrase CD quality sound. So people my age kind of remember that in the 80s, that was a big phrase, CD quality sound, meaning that, hey, it sounds as good as a CD. Well, the standard for CDs, right? They're like, well, which frequencies, would it be okay if our recording mechanism failed at certain frequencies? Because all recording mechanisms do, right? There's a point when they can't respond to the frequencies appropriately, and they're like, okay, well, this 20 to 20,000 hertz, let's remember that. Let's make sure that 20,000 works fine. In fact, let's round that up, but let's go to 22,000, right? And so a lot of you know, when it comes to sampling, there's this 44,000 something, I forget exactly the exact details, but 44,000 samples per second is what's called CD quality sound. And there's this theory called the Nyquist limit, blah, blah, blah. But the fact is your sample rate determines the frequencies that are going to be accurately portrayed, accurately measured. And it turns out you just have to divide your sampling rate by 2, and you get the highest frequency that works. So 44,000 divided by 2 is 22,000, right? I don't think there's a single human who can hear, frankly, I have never met one who can hear 20,000, but 22,000, they felt that's safe. If we do that, our CD quality sound is going to be awesome. And what I love talking to students about is exactly what she's saying right here, right? Well, dogs can apparently hear higher than that. Well, how much higher? How much of those frequencies way up there are they using to discriminate things? And so my question, I guess I've never really tested this, but CD quality sound of recorded dog barking likely is not an accurate measure of the full frequency range that dogs can actually hear and are used to hearing. So do dogs notice the difference, right, of a recorded dog bark in CD quality sound? I keep saying that because it's not perfection. It's just choices that they made in the, late 70s, early 80s. So I think that this idea of the range of frequencies you can hear is just super, super fascinating. I was going to say one more thing about dogs. Shoot, I can't remember what it was. Oh, I know what it was. So there's other recording technologies that have way less quality. So sort of old style phone connections, not the new digital phones, but the old style phones, I think their cutoff is something like 5,000 hertz. That's it. And why? Because they were simply intended to communicate voice. That's it. You're not really supposed to sing over the phone. You're not really supposed to play music over the phone. In fact, if you think you have an old style sort of analog phone, not digital, play some music through it and you'll realize, oh yeah, I know that sound. It's a very recognizable sort of tinny, well, tinny is probably the wrong word. Just there's clearly some filtering going on. And so it kind of depends what you're trying to measure. And so for me, if I'm building something for myself, I know I can't hear above, 14,000 hertz. Why should I bother recording it any higher than that? All right, I think actually I'll stop there. This is super, super great. I loved this. It sounds like it was maybe the first lecture about sound. I loved how she was connecting to the previous work. I loved the visuals, super great. And the connections to their lives. I thought that was really, really great too. So thanks a lot, everybody. Have a great day. And remember, physics teachers are awesome.